Okay. Time seems to be flying by. We're going to wrap up our Haskell lectures today, and then for the rest of class, we've got just 2 weeks left. I mean, it's pretty amazing, but we've got 2 weeks, exactly 2 weeks of class left, so 6 more lectures. And we'll be covering a bunch of miscellaneous topics. Just a note that your lazy programming assignment, so this is your second to last lab, is due on Monday. So I didn't really want it to be due on Saturday because general conference and all that. I'd rather have you guys thinking about conference and just enjoying it. So lazy programming due on Monday. At this point, you should have enough Haskell foo to be able to do it. Of course, if you have questions, please let me know or let the TAs know. I think it's a fun one because you end up using the laziness of Haskell to build some pretty cool data structures to help you calculate an infinite list of primes quickly. So good luck on that. And if you have questions, please come prepared on Friday with any questions that you have, unless you have questions now. If not, then we'll go ahead and dive in. So we're going to try to finish our lecture on monads. And I need to maybe preface this lecture with a disclaimer. I always hate to manage expectations down, but to me, this is the hardest lecture that I give all semester. And what I mean by that is it's hard because I feel like it's conceptually difficult, and I try to spend a lot of time reading about monads and trying to understand why they're useful and what the big deal is. But it's also hard because I've had a hard time. I think I've got an idea of why they're cool, but then I have a hard time distilling that into something coherent that I can get across in a 50-minute lecture. So that's why this is hard. So stick with me. I think there's some valuable things here, and hopefully it'll be useful to you. At least, hopefully you won't be scared of the word monad, and you'll maybe sense that there's something useful and deep there. And for those of you that are more interested in the theoretical aspects of computer science, hopefully this will be just a little teaser, and you'll be like, oh, that's really intriguing. I'd like to learn more about that. Okay, so think of this as more like a trailer for monads. It's like an advertisement for monads. And maybe you'll go watch the movie. Okay, so let's go ahead and dive in. So we're trying to talk about monads. There's a lot of different ways to motivate monads, and you can find a bunch of these on the internet as you Google around. One way to think about monads is as composable computations. Another way to think about it is you use monads as just a sort of an interesting way of eliminating boilerplate code. Some people really like this. There's a super strong link between monads and category theory, and you get lots of interesting, kind of powerful stuff as a result. We won't unfortunately cover that today because I frankly don't understand it very well. Certainly one practical benefit of monads is that it lets you separate concerns through abstraction, and we'll try to go through an extended example where I illustrate that. And then practically, as we talked about in last lecture, you can use monads to isolate side effects, such as I/O or mutation, and that can give you the benefits of a purely functional language that actually does stuff. And that's, I think, one of the primary motivations for monads in languages like Haskell. But the functional programming community is pretty excited about monads. I mean, they've been around for decades, but I'm pretty excited because they seem to solve a lot of interesting problems in a very elegant way. And the fact that they're mathematically sort of powerful, I think helps people to feel confident that they're kind of, in some sense, the right thing. Okay, so what is a monad? Well, we've talked a little bit about, we've used all these pictures to try to go through functors and applicatives. So just to remind ourselves, so a functor is, it's a type class that knows how to, it's type that knows how to apply a function to a wrapped value. So you've got some function, single parameter function, and you've got a wrapped value, and a functor knows how to unwrap the value and apply the function. And then applicatives, similarly, applicatives can unwrap a function and apply it to a wrapped value, and like smart enough to do that. And a monad is kind of like the next logical generalization of this. So monads apply a function that returns a wrapped value to a wrapped value. And what this is going to let us do is compose wrapped values and computations together in a very natural way. And it's this idea of composing wrapped values that I think is at the essence of monads. So to me, when I think of a monad, I think of there's some data, which we're calling these wrapped values, and there's some context, which we're representing as these boxes. And what monads allow us to do is thread our computation, like think of our computation as flowing through a program, and think of some sort of context as flowing alongside it. And monads will let us do that in a very natural way. So let me talk just a little bit about this perspective when we think about I/O in Haskell. So I tried to make the argument last time that if you have a functional language, it has to have side effects to be useful. And I/O is one of the most important side effects. So how can you make a function that does I/O look like it's deterministic and looks like it's functional? And the answer is, so imagine reading from a file. So the way you can do it is you can think of the world as, or the state of the world as an extra input to an I/O function. Because then the I/O function is deterministic. I take, like, for example, I take the name of the file, and I take the state of the world, and I put them both in to this function, and it goes ahead and reads from the file and returns some value. And if you plug in the same name of the file and the same state of the world, you'll always get back the same result. So this idea that you can think of, you can make I/O look deterministic by threading the world through your code, to me makes a lot of sense. I'm like, oh yeah. And in Haskell, the idea of threading the world through your code, along with the computations that you're trying to execute, is accomplished with a monad. So a monad is this thing that takes the values, which are the things that your I/O operations are returning, and it's taking this context, which in this case is the state of the world, and it's threading those things through in kind of this sort of elegant way. But we'll see that monads are a much more general concept. So here we're going to start off with a couple of examples. So here's a little function called half-x. So half-x is a little function. You give me a value, and if it's even, then I'll divide it by 2. Otherwise, I'll return nothing. So this will only give you, it's sort of like integer division by 2 with error checking in case you're not divisible by 2. Okay, so this is using the maybe monad. So it's, if it succeeds, and it returns just the correct value. Otherwise, it returns nothing. Okay. And yeah, hold on just a second. Get out of laser pointer mode. Oh, whoops, that's not what I wanted to do. So sorry. Give me a second. I was just trying to get our chat window out of the way. Okay. So this function, takes as input a value, and it will return as output a wrapped value. So notice that it returns an instance of the maybe monad. So it returns either a just or nothing. So in Haskell, in order to make sure that a type is monadic, you need to define a couple of operations on it. One of them is called bind. And bind is typically represented with this greater than equals sign. And this is like a cartoon picture of what bind looks like. And the reason it looks like a plunger is because you can pull stuff out and you can jam stuff in. And that's what we're going to be doing. So here's some examples of this half function in action. So if you, and here's what happens if you use this bind operator. So notice that half x, it doesn't look like it knows how to, it looks like you have to just pass in an integer, right? And here we're saying, take a wrapped integer and use this bind operator, and it sort of looks like a pipe, and pipe it to this function, and we get the right answer back out. So somehow this bind operator is like unwrapping this, passing it to this function, taking the result and returning it. So monads is like helping us compose some things together. Kind of looks like this. So what bind does, and this is why it looks like a plunger, what bind does is it unwraps the value, feeds the unwrapped value into the function does its calculation and spits out a wrapped value. And of course, if you plug nothing in, then nothing comes back out. And what's great about the bind operator is that you can compose it. So you can sequence operations using many applications of the bind operator. So this is kind of like piping that we saw in Elm, except there's a lot more crazy typing that's going on under the hood. So don't exactly think of it like piping, but it is close. So here, for example, I'm taking a value 20, I'm wrapping it up in a just, and then I'm using bind and I'm passing it into this half function, and the half function passes the result to the half function and the result to the half function, etc. And because 20 divided by 2 is 10, and 10 divided by 2 is 5, and 5 divided by 2 is not divisible by 2, you end up with nothing at the end. Why does the first plunger have a hand? I don't know, Eric. Sorry. Because that's what the blog post had that I copied it from. Okay, so here's a little snippet of the type class definition for monad. So a monad, so you remember that M here is a type variable. So this is like remember this is like what's called a type class definition for monad. So think of it as an interface, if it helps. So anything that is a monad has to implement this thing. So what is this thing? This thing is the bind operator. And you give it a wrapped value of some type A. So this might be just an integer. And you give me a function that takes an A and gives me a wrapped value of type B. So this might be that half function, which accepts as input an integer and returns a wrapped integer. And the result will be a wrapped value B. Okay, so that's actually pretty straightforward. Like it's just so bind is a 2-parameter function that returns a single wrapped value. Yeah, I guess we said that. So, monads more generally, you need sort of some way to kickstart the process. And so monads are generally represented with 3 parts. There's this thing called a type constructor, the bind value, and then a combinator. So let's look at maybe. So I keep referring to the maybe type as a monad, and that's because maybe is a monad. And that's because it implements the, I'm not using these words super precisely, but it implements the monad interface. So let's look at the definition over here of maybe. So this is saying that maybe is an instance of monad. And so this code is describing how the maybe type implements the monad type class. So it's saying, here's the definition of the bind operator in the context of a maybe, which is if you give me a wrapped value, so if you give me just an x and a function k, then the result of applying that function to something that's wrapped up in a maybe value is just applying the function k to the unwrapped value x. So it's very simple. Similarly, if you give me a nothing and you give me a function, and the function doesn't matter what the function is, then the result is nothing. Okay, Andy, yes, question.
Could you review what a wrapped value is? I'm a bit lost on that.
So a wrapped value is just, think of the maybe. Think of the maybe value. So if you have a function that returns a maybe, something that's of type maybe, then it's going to either return just the value or it's going to return nothing. So when we say just the value, it feels like the value is kind of wrapped in this just thing. So that's what we mean by a wrapped value. Does that help?
Kind of. I'm trying to, in my mind, separate it from casting. I guess that's right. I keep thinking of it as casting. I guess
Yeah,
maybe that's not quite correct.
It's not casting. It's not casting because you're not changing the type of the thing. It's like you're taking a thing and you're wrapping it in a new object. So the original thing is still there. It just is like inside of another object. Let me see if our examples. I have this extended example that I think might help us to understand kind of why this is helpful. So let me first just point out. So Andy, hold on to your question, and if you have a question, please feel free to ask it because I mean, if I don't answer it at the end of this extended example, okay? Because I'm hopeful that we'll all understand this at the end. So by the way, so lots of different types are monads. So for example, lists we already talked about as functors and applicatives, but they're also monads. Lots of interesting things can be implemented as monads. Okay, but let me go through an example. So I think that hopefully this will give us some clarity as to why monads might be useful and what I mean when I say wrapped values and what I mean when I say composable computation and what I mean when I say separations of concern and abstraction. Okay, so if the first part of our lecture today hasn't done it for you, then hopefully this part will. So let's, we're going to imagine a little sheep genealogy application. This is not my example. I got this from the internet, but I think it's fantastic. So let's imagine that I define a type called sheep, and it's got, I don't know, it's got some values in it. The actual details here aren't important. But we have a function. So we've got the type of sheep, and we've defined some functions that involve manipulating sheep in different ways. And since we're building a sheep genealogy database, maybe we'd have some like functions that help us reason about sheep lineage. So for example, you can imagine a father function. So the father function takes as input a sheep and returns a maybe sheep. So why would it return a maybe sheep? Well, a couple of reasons. First of all, maybe our database is incomplete. And so maybe for a given sheep, we don't know who that sheep's father was. Or maybe in the weirdest case, we're like doing, I don't know, some sort of genetic cloning and the sheep doesn't have a father, okay? But either way, you can sort of imagine situations where the father of a given sheep is not defined. So this function will return a valid sheep if the father is defined, but it could also return nothing if we don't know what the sheep's father is, okay? Similarly, you could imagine defining a mother function. And the mother function takes as input a sheep and returns a maybe sheep in case we can find the sheep's mother in our database. Okay. So let's imagine now some more complicated functions. So let's imagine a maternal grandfather function. Well, if we have a maternal grandfather function, so this is also going to take as input a sheep and will return a maybe sheep. And the result of this this function takes a single argument s, which is a sheep, and the body of the function looks like this. So we're going to ask, well, in order to determine the maternal grandfather of the sheep, the first thing we need to do is look up the mother of the sheep. Now we know that if we call the mother function on a given sheep S, it might return a valid sheep, but it might also return nothing. So in the case that the mother of S returns nothing, then we want to return nothing. Straightforward enough. I mean, if we can't look up the mother, then we can't look up the maternal grandfather. But if it returns just M, in other words, if it returns a valid sheep, which we've called M for mother, then we want to return the father of M. Okay, and that'll give us the maternal grandfather. Of course, father of M could return nothing in case we can't look it up, but it could return something. But in either case, this is valid. Okay, so hopefully this looks pretty straightforward, like little case statement and no problem. But notice that we've got this little bit of logic in here, which is that if mother returns nothing, then we sort of can't go any further. We just have to return nothing immediately. Okay, so what if we wanted to extend this just a little bit? And what if we wanted to create a function called mother's paternal grandfather? So this is a fantastic function. It's just one extra step of logic from our previous function. So it again takes a sheep as input and returns a maybe sheep. We're going to look up the mother of the sheep, S. If it's nothing, we'll return nothing. Otherwise, if we get back a concrete sheep, then we'll look up the father of the sheep. And that might return nothing, in which case we want to return nothing. But otherwise, we want to pull out whatever the grandfather is and then ask what the father of that grandfather was. And then that'll either return nothing or a true sheep. Okay? So hopefully you can see that there's a bit of a pattern emerging here. And also the code is getting kind of ugly. So the pattern is anytime there's a nothing, it like torpedoes the entire calculation. Like we just can't proceed and the result will always be nothing. And you can also see that this feels a lot like the same logic is being iterated over and over and over again. So you might look at this code and think, well, this is certainly correct, fine code, but it feels ugly. And is there anything that we can do to simplify it? And this is where monads come in as something that's practically useful to help us abstract computation and therefore simplify our code. And the thing that we want to abstract is the way we handle nothings. Basically, wouldn't it be nice if we could just say, look, if the result is ever nothing, then the entire computation is going to be nothing. Like, it feels like we just want to say that once and not repeat that idea again and again. So to do this, we need a little bit of help. And what we're going to do is define a little itty bitty monad that's going to help us out. Okay? So we're going to define an operator called comb for combine. And the idea is the following. So we're going to define a little function, and it's going to take as input a maybe and then some sort of value, like a sheep, like maybe a specific sheep. It's going to take one of those in along with a function that processes something, processes things of that type, and returns a maybe, and then returns a maybe. And if it ever sees a nothing, then it's going to return a nothing. And if it ever sees a valid something, then we'll go ahead and apply this function f to that thing. And so now, if we look at our code, here, a second, okay, I'm turning off my little chat windows. Now, if we look at our code, we can use that comb operator, this combine operator, to simplify our code. So here's mother's paternal grandfather of S. And look what happened. So we take S, which is a sheep, and we first sort of wrap it in just. So we're gonna assume that they've given us a valid sheep to begin with. So we wrap it up in a just. We then take that and we apply it with the combine operator and the mother function. So the mother function is handed up here. It's this thing right here, right? The mother function takes a sheep and returns a maybe sheep. So we combine the wrapped sheep with the mother function, and we use this combine operator to say, well, if it's nothing, then we'll return nothing. Otherwise, if it's just a sheep, we'll go ahead and ask what its mother is and return the result. So this little bit right here will become either nothing or just a sheep. And then that will be combined with the father operator. And that will result in nothing or just a sheep. And that will be combined with the father operator, which will be nothing or just a sheep. So in this way, look at how we've dramatically simplified the code, and we've abstracted out the logic of, look, if there's ever a nothing, then the result is going to be nothing. Now, this combine function, notice this combine function actually isn't specialized towards sheep at all. You can see it's completely type generic. And this little function is capturing a general strategy for combining these computations that may fail to return a value. And you could use this little combine thing with other functions. Like it doesn't have to do anything with sheep. It's a very general sort of thing. And in Haskell, this little combine thing is exactly an instance of a monad. And if we go ahead and actually call it a monad in Haskell, then we get a few things for free. In particular, Haskell has support for these monads built into the language and gives you some little syntactic sugar to help you write cleaner code. And in particular, you can define, if you define something like the maybe monad using this syntax, so we make sure that maybe it's not just an algebraic data type, but it's actually, we actually tell Haskell, no, this is a monad, and we give it a specific, and we like define this operator, this bind operator, and we also define a special thing called a return. Then all of a sudden we get to use this kind of cool syntax. So here's what it looks like. We can now use these monadic operations to compose computation together. And what we're doing is we're threading. So like I said, I wanted to take the perspective that what monads are doing is they're threading calculations through a code. They're also threading context through a code. And those two things are being threaded together. And in this case, we're threading a sheep, and we're threading sort of whether or not there's been an error in looking sheeps up. We're threading those two things together, and we're composing sequences of computations together in a unified way that lets us fail at any time in a very clean way. Okay, so let's just take a look at this definition really quickly. So we're saying that we've talked about maybe as just an algebraic data type, which is either nothing or just a thing. But here we're saying, no, it's more than that. We can actually define it as a monad. So if we ever see a nothing, and we see the bind operator, and we see a function, then that is going to be equal to nothing. If we ever see just a something, for example, just a sheep, and we see the bind operator, and we see an f, then that is going to be equal to applying the f to the unwrapped value. And if we ever see the return keyword, then that's equal to the just keyword. And this is the way that we bootstrap the process and wrap something for the first time. So let's see what that looks like down here. So now we can rewrite maternal grandfather S using the following, I think, super elegant code. Return S, what that does, so what is return equal to? Well, return is equal to just. So this is going to be just S. So we're going to take S, wrap it up in a just, and then the process will begin. So now we have just S, we see the bind operator, and we see a function called mother. So we look at our pattern matching, and we see, where does that match? Oh, that matches right here. Just a sheep, bind operator, and then some function F. Well, that is equal to, we apply the F to the X. So we're going to unwrap the sheep, apply the function to the sheep, and then this function needs to return a wrapped value, which it does. And so the return value will either be nothing or a wrapped value, which we can then combine with father, etc. So to me, this is beautiful, because what this is saying is we've abstracted out the error checking, and we only write the code logic for error checking once. And it's right here in our definition of the monad. And we've separated, and actually, this may be definition, this is like super generic. This also doesn't have anything to do with sheep. And we could use it all sorts of places. So anytime we need to thread error checking with computations that might return, that could potentially return error values, we can use this maybe monad. So it's a very generic solution to the idea of threading an error alongside of computation. And then finally, of course, father's maternal grandmother, like this is even more concise, like way more concise than our previous code. So it's like super elegant, in my opinion. Okay, so I hope that that was at least a little bit clear. At this point, I would love to just hear if there's any questions. Like I said, I know this lecture probably feels a little crazy and a little out there, but I'm trying to maybe convey the sense that not only is this an interesting mathematically principled thing, it's also a practically useful thing that lets you write pretty clean and streamlined code. I mean, I don't know, are we getting it? Eric, go ahead.
Sorry, I was trying to write out the question in the chat rather than stating it. Is that how it's written though? You say instant monad maybe where and then nothing bind f equals? Or are those equals even there?
Yes. No, this is literal syntax.
Okay.
This is, I think there might be one or two other lines that you need in order to completely define the maybe monad, but it's literally just this. So it's pretty straightforward. Any other questions about this? Okay. Oh, so I got something here. Sorry, it's in the chat. Jake asks, I'm confused how this relates to helping Haskell have positive side effects. Maybe I don't understand what we mean by side effect. Okay, yeah, so the question is, well, okay, so how does this idea that we can compose computations together, like how does that help us with having, like getting around the idea that a functional language needs to have side effects? Well, this is what I was trying to explain at the beginning. And as I said, like one way to make your program perfectly functional, even in the presence of, for example, I/O, is to thread the world through your code. Thread the state of the world through your code. But that's really hard and would be very painful. And it would feel kind of like threading things that like threading maybes through your code, where you'd have to have sort of the state of the world would have to be passed around through all of the functions, and you might be having to constantly check the state of the world for errors, etc. And what monads lets you do is two things. First of all, they make it easy to build code that relatively transparently threads the state of the world through it, but also helps you sort of encapsulate the state of the world into a well-defined box that I think, anyway, I'm not an expert, but I think that the Haskell compiler can then, as I said earlier, can sort of make sure that it knows, okay, here's all the IO, here's all the bits of your code that depend on IO, here's all the bits that don't. I hope that's clear. I don't know, does that answer your question? So in this case, Jake continues, in this case, the state is whether our sheep is real or nothing. Yes, exactly. Great. Okay. So let's see just maybe a couple more examples. Let me, so if you have a question, well, here, I just have to move my windows around a little bit. So you also get some other syntactic sugar for free. And you get this thing called do notation in Haskell, which can be helpful and can also simplify the writing of code. Oops. And what it lets you write in is a pseudo imperative style, and you can easily get these named variables in Haskell. And basically, you can use these arrows to define complicated sequences of calculations in kind of a monadic way. So here's, we can rewrite our, as long as sheep and maybe is a proper monad, then we can go ahead and rewrite our code in this way. So we can say, well, let's get the mother of S and apply it to M, and then let's get the father of M and call that GF, and then go ahead and take GF and ask what is the father of that. And this is just syntactic sugar for what we've seen before, where the values will get threaded properly through. But it just looks a little bit more like an imperative style of programming. So it might be a little bit cleaner to code this way. Let me give you another example that I hope is useful. So we've seen interpreters, and we've written interpreters in this class, and we've written, we've seen how little expressions and expression evaluators can be written. So let's see what it might look like in Haskell. And what we'll see is there's a very similar kind of error that can happen in an arithmetic evaluator. And you might want to thread the error checking for that condition throughout your code. And you can do it in a pretty easy way. So let's take a look at this very simple expression evaluator. So we've got this type, which is called EXP. And you can have plus 2 expressions or minus 2 expressions or times or divide or just constant integers. And so if we wanted to evaluate something, so evaluate is a function. I'm going to bring up my laser pointer. Evaluate is a function, and that function takes as input some expression and gives back as output some integer. And here's all the pattern cases. So if it sees eval and it sees a plus and it sees 2 sub-expressions, then the result of this is just we evaluate the left-hand side, we evaluate the right-hand side, and then we add the 2 together. Same thing is true for minus, times, and divide. And if you ever see a constant integer, then the result of the calculation is just an integer. And so we can go ahead and we can, like using this very simple little expression syntax and these types, we can go ahead and create little expressions like div constant 3 plus const 4 plus const 2, and you'll get some answer. Okay, straightforward enough. So hopefully this makes perfect sense given what we've seen so far in Elm and in Haskell. But what if we wanted to add error checking? Well, like maybe divide by 0. What if we wanted to add error checking for divide by 0? So if we wanted to use pure functional languages, we would have to basically modify every recursive call, and it would have to check to see if any of the sub-expression evaluations resulted in an error. And if they did, then it would throw an error. If you want to do it impurely, of course, you can just throw an exception. By the way, notice that if we wanted to add logging to our little expression language, and we wanted to do it purely, like if we wanted to, for example, I don't know, like log all of the intermediate calculations that we generated along the way, well, we'd have to like somehow thread a logging accumulator throughout our code, and every recursive call, we would have to also have a little log object or log data structure, I guess, that we'd update. And of course, we could do it impurely, and we could just like write to a global variable, and that would be awesome. Or maybe we want a profiler. And so if we wanted to add a count of the number of operations, well, if we wanted to do it purely, we'd have to modify each recursive call to count things and accumulate them. Of course, if we want to do it impurely, we could just increment a global variable. So the point of this little example is just to show that there's this general pattern here of things that are awfully easy to do in impure ways. And if you're going to do it purely, it feels like, oh man, I have to like thread something through my code in order to get it done. Well, this is where monads might be useful. Monads might help us to thread the error or the log or the count through our code, and hopefully our final code won't look much more complicated than this. This is really beautiful and really simple. But if we had to like thread logging operations through this, it would look a lot more ugly. So let's see if we can do that with some sort of monad. And what we could do is you might say, okay, let's think about error handling for a second. Let's think about division by zero. Let's define something called a hope monad, or sorry, a hope algebraic data type. So hope A, it's either going to be an OK value or it's going to be an error, and it'll have some string associated with it. So for example, let's think about our evaluator in the case of division. So in the case of division, you give me two expressions, the numerator and the denominator. And so I'm going to go ahead. Oh, sorry. So the signature now of eval is you give me an expression and I'll give you a hope integer, meaning that I'll either give you an integer back or I'll give you an error back. Okay, so the case of div, I'm going to go ahead and evaluate the first expression. So that might return, that's going to return a hope value. So it'll either return OK and a value, or it will return error and a string. If it returns error and a string, then I just want also to propagate that. So I'm just going to return error in the string. But if it returns OK, then I'll go ahead and evaluate the second expression. Evaluating the second expression could return OK, but it could also return an error. If it returns the error, I just want to propagate the error. But if it returns OK, then I need to actually check to see what the value of the second expression is. If it's 0, then I want to return an error. But otherwise, I want to return an OK value with the actual number. So this is like super ugly, right? Because I have to be constantly checking for the presence of errors in case I want to short circuit my evaluation. If anything goes wrong at any time evaluating something, then the whole calculation is going to blow up. So I want to be able to cleanly propagate that error. And this is where you might want to use a monad to help you thread this error condition through the state of your program. And so you could use a little higher order function called if OK then that takes a hope and a function that operates on a value and returns a hope and returns a new hope. And the definition is very simple. It's if you give me some expression, I'm going to ask if it's OK. And if the result is an OK, then I'll go ahead and apply the next function. Otherwise, I'm going to return an error. If you define this little if OK then function, then all of a sudden your code simplifies quite a bit. And notice that the definition of this if OK then function looks a lot like the definition of monads that we've seen before, of the bind operator in monads. And that's not surprising because it's doing exactly the same thing. And so we could actually expand this and actually do it with a proper monad. But let's just really look. Oh yeah, so if we do it with a proper monad, then, oh shoot, I don't have it. Oh, I thought I had the slide where we could actually rewrite this using using the Hope monad more properly. But basically, you get to get rid of all of this gobbledygook. So oh, this already looks cleaner though. Hopefully you can see that. So here's, for example, here's our divide function. So we've got the numerator and the denominator. We evaluate the numerator. We ask if it's okay. If it is okay, then we go ahead and take the resulting value and we evaluate the denominator. If it's okay, then we go ahead and give it a name for the resulting value, and then we ask, do a little bit of error checking on the results. And if we just go ahead and rewrite this as a full monad, then we can use the do notation, or we could use the little bind operators composed together to simplify our code even more. So this is just one example of how you might want to thread an error condition through your code. All right, amazingly enough, we're out of time. Wow, things seem to go so fast in this new format. So hopefully this was okay for you. Hopefully you learned something about monads. I hope it was useful. And hopefully, like I said, you got a little flavor of what's going on. And hopefully for those of you that are more mathematically oriented, you might start to sense that there's something actually really cool and deep here about this. So I think that's all we're going to do. Take care. Good luck on your Haskell Lazy Programming assignments, and we'll see you on Friday. And now I'm going to stop sharing.